Section 3.5, Absolute Maximum and Minimum. In this section, we will find the absolute maximum and absolute minimum of a function and determine maxima and minima in real-life applications. Absolute extrema. If C is in the domain of the function f, for all x in the domain of f, we have 1. If fx is less than or equal to f at c, then f at c is called the absolute maximum value of the f of x. 2. F of x is greater than or equal to f at c, then f at c is called the absolute minimum of the function f. In a graphical way, if you have the curve at the point c, the function value c is greater than or equal to all function values of the x within the domain. F at c is called the absolute maximum of the f. Similar to the absolute minimum, at the point c, the function value at c is less than or equal to all the function value of the x within the domain. F at c is called the absolute minimum value. The theorem of absolute extrema of a continuous function. If the function f is continuous, that means you have the smooth curve on the closed interval AB, then f has an absolute maximum value and an absolute minimum value on the closed interval AB. To find the absolute extrema of a continuous function on the closed interval AB, step 1, we find all critical values on the closed interval AB. That means you are going to find the derivative and let it be 0 or let it be undefined, or look for the cases to see will give you the slope 0 or the slope undefined. Step 2, evaluate the function value at two endpoints, or function at A, function at B, and the function value at all critical values C that you found from step 1. Step 3, the largest value found in step 2 is the absolute maximum. The smallest value found in step 2 is the absolute minimum. Example 1. Find the absolute extrema for the function f of x equals 2x to the third minus 15x squared plus 24x plus 6 on the interval 0, 5. In this case, a equals 0, b equals 5 are two endpoints of the closed interval. The function is polynomial, and all polynomial function is continuous. So that means it satisfies the theorem for the absolute extrema for the continuous function on the closed interval AB. Step 1. We're going to find the critical value. To find the critical value, we have to know what is the f prime. For this function, the derivative of the f prime is 6x squared minus 30x plus 24. This is a polynomial function again, so it will satisfy the case that f prime of the c equals 0 is always defined within the domain, which is the set of all real numbers. So the critical values can be found from letting f prime of x equals 0. We're going to solve for x for this quadratic equation. Factor 6 out, we have 6 multiplied by x squared minus 5x plus 4. And in factor more, we have the factor x minus 4, x minus 1. Therefore, we have two critical values, x equals 4 and x equals 1. Step 2, we're going to find the function value at two endpoints, which is at 0, at 5, and at all critical values that we found in step 1. So f at 1 and f at 4. To find the function value, we place x with the value 0, 5, 1 in the original function. So for f at 0, 2 times 0 minus 15 times 0 plus 24 times 0 plus 6, we get the value 6. For f at 5, 2 times 5 to the third minus 15 times 5 to the second plus 24 times 5 plus 6 equals the value 1. For f at 1, 2 times 1 to the third minus 15 times 1 to the second plus 24 times 1 plus 6 equals 17. F at 4, 2 times 4 to the third minus 15 times 4 to the second plus 24 times 4 plus 6 equals negative 10. And then step number 3, we look at the largest quantity that we found in step 2. For this case, 17 is the largest quantity. Therefore, f at 1, which is 17, is an absolute maximum value for this function. And the lowest number or the smallest number is negative 10. So f at 4 equals negative 10 is an absolute minimum value for this problem, for this function. I will look at the graph. The two endpoints at 0 and at 5, the function value at 0 is 6. The function value at 5 is 1. The two critical numbers, x equals 1 and x equals 4, the slope 0, or the tangent, the horizontal tangent at the point x equals 1 and x equals 4. The function value at 1 is 17. Function value at 4 is negative 10. So we have the graph that looks like this, that show that x equals 1 gives the absolute maximum value. At x equals 4 gives the absolute minimum value of this function. Next example, we have the f of x in the form of x to the 2/3 plus 1 on the interval negative 8, 8. Our a is negative 8, the b is positive 8. Step 1, find the critical value. It could be more than one numbers. Find the first derivative, which is 2 over 3 x to the negative 1/3, or 2 over 3 times the cube root of x. To find the critical values, the first case, f prime at c equals 0. This case, we consider the numerator equals 0. In our case, 2 is not 0, so no critical value coming from the case at f prime at c equals 0. The next case, f prime at c is undefined. For the undefined case, we look at the case at denominator equals 0. In this function, the f prime of x, the denominator is 3, the cube root of x equals 0. Therefore, we get the x equals 0 as the critical value for this function. Step 2, find the function value at two endpoints, f at negative 8, f at positive 8, and the function value at all critical values, which is x equals 0 for this function. So f at negative 8 is negative 8 to the power 2/3 plus 1, and gives us positive 5. For the value 8, f at 8 is 8 to the power 2/3 plus 1. Also give the number 5 as a function value. F at 0, 0 to the power 2/3 plus 1 equals 1. In step 3, we can see that the number 5 is the largest number or the largest value. So f at negative 8, f at positive 8, which is given the value 5, is an absolute maximum value for this function within the interval negative 8, positive 8. And then positive 1, or the function at 0, is an absolute minimum value for this function. As you see the graph, the two endpoints at negative 8 and positive 8. Function value at those two endpoints are 5, the same value. The critical number appears at 0, and at the point 0, we have the vertical tangent.